This is the Chem 1 lecture over periodic trends, part 2. So last time we talked about atomic radius and ionic radius. This is we're going to talk about 4 new trends, the first one being ionization energy, abbreviated IE. It's the energy required to remove an electron from an atom. So if you want to walk up to an atom and take its electron, how hard is it going to be for you to take that electron? So, if you're removing an electron, you're forming a positive ion. So, who would you predict, before we even look at this trend, to have low ionization energy? Who is already trying to get rid of their electrons, and if you walked at them and tried to take it, they'd be like, yeah, sure, here you go. Metals or non-metals? Who's already trying to lose electrons? Metals, absolutely. Metals are already trying to lose, so you can probably predict that they're going to have low ionization energy. Whereas, who do you think is going to have high ionization energy? Who's trying to gain electrons, therefore does not want to lose them at all? Non-metals. Yeah, non-metals are trying to gain some more electrons. So if you walk up to them and you try to take theirs, they're going to be like, no. My analogy is, for example, I'm a metal. I have 3 ACL tickets I'm trying to get rid of. If you walk up to me and I'm desperately trying to get rid of these 3 and you say, hey, I'll give you $50 for each of those, I'm probably going to sell even if I'm losing money, right? Because I want to get rid of them. I want to make some money off of them. Whereas if I have 8 friends, but I only have 5 ACL tickets, and you walk up to me and go, hey, I want to buy an ACL ticket from you. Am I going to sell one of my 5? I'm trying to get how many? 8. So if I sell you one of my 5, now I have to find more, right? Doesn't make any sense. So since if I'm trying to find more, it's very unlikely that I'm going to give up any, and that's exactly how nonmetals are. So the general trend for ionization energy, this is a graph showing you these things. Let's talk about going across a period. So within one energy level, which one do you want to do? Energy level 1, 2, 3, 4, 5, 6? Which would you prefer? Energy level 4, beautiful. Energy level 4, if you look at the periodic table, is potassium, calcium, gallium, germanium, arsenic, selenium, bromine. Let's see, here they are. Potassium, calcium, gallium, germanium, arsenic, selenium, bromine, krypton. In general, what's the trend you see going across a period? It's getting higher. It's increasing. That's that general trend you see right there. Now let's think about this in terms of nuclear charge. As we go across the period, are we holding on to our electrons tighter or looser? Tighter. And so don't you think as you go across, it'd be harder and harder to remove them if I'm holding on to them tighter and tighter and tighter? Absolutely. Let's talk about down a group now, shall we? Pick a group. Group 1, Group 2, Group 13, 14, 15, 16, 17, 18. Which group do you want to do? Group what? 13. Sounds good. So going down group 13, it's boron, aluminum, gallium, indium, and thallium. So let's find them. Boron. Oh, this is a fun one. Boron, aluminum, gallium. What's after that? Indium. Oh, I don't think the next one's there. Thallium. What's the general trend you see here? It's hard to see, especially in that group. It's decreasing. It's much easier to see if I had chosen group 18, but I let y'all pick. You can definitely see it in group 18. So going down a group, it is decreasing. Let's think about what's happening as we go down a group. Our electrons are getting further and further and further and further away from the nucleus, right? We're adding energy levels as we go down a group. So what this means is if I was holding this electron, this pen in my hand, and I'm holding it like this, nice and close and tight to my body, easy or hard for you to take it away? Hard. It'd be hard for you to take it away. Lots of energy for you to remove this from me. It's like pry it from my cold, dead hands, right? But if I'm holding it out here and I'm talking, I'm like, la, 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 la. Easy or hard? Easy. Same exact idea. As you go down a group, the electrons are getting further and further away from the nucleus. It's much easier to come take one if it's being held away far from your body or far away from the nucleus. So let's draw these trends on our periodic table. Going down, we said it decreases. And going across, it's going to increase. What about removing a second electron? So you take your first one. What's the charge going to be? If I remove an electron from you, your charge will be +1. So if you have something, and I'm going to call it element X, and it takes, give me a number. What's your favorite number, Carly? 13? It takes 13 kilojoules of energy. I just totally made that up for element X. 13 kilojoules to remove one electron. And now I just did that. I paid that 13 kilojoules of energy. Now I have a +1 charge. Is it going to be easier or harder now to remove another electron if it's a +1 charge? What happened to my nuclear pull? What happened to my ratio of protons to electrons? Do I have more protons or more electrons? More protons. So they're pulling more. Remember that atom got smaller because it's a positive cation. So is it going to be easier or harder to remove another electron? Harder. It might be $50, 50 kilojoules worth of energy before you remove that one. What about if I want to remove the second one? I need to remove, it's going to be harder, maybe 100 kilojoules of energy to remove that one. You guys see that trend? Now, the second ionization energy will always be greater than the first. The third ionization energy will always be greater than the second. Fourth, always greater than the third, so on and so forth, because you're becoming more and more positive. Therefore, you have more and more protons pulling on less electrons. Well, you actually have the same number of protons, just pulling on less electrons. Here's the cool thing about this is you can determine some things by it. Let's look at an element in group 2. Let's look at beryllium. How about that one? Be. It's got 2 valence electrons. I'm going to draw a Lewis dot structure for it. Notice I put the first 2 together, right? Because those are those S elements, S1 and S2. Okay, making this number up. I don't know. Let's use the same numbers that she used up there. 13 kilojoules. All right, I put in 13 kilojoules, and I'm able to remove that and become beryllium +1. It's going to cost me a little bit more to remove the second one, okay? So 50 kilojoules for the second one, and now I'm beryllium +2. We know the third energy level is going to be greater, right? But watch what happens. 10,000 kilojoules of energy to remove a third electron. Why do you think that's the case? Why did it jump up so high? Because you had to go into a lower energy level, exactly, and that energy level you went into was full. And remember, that's stable. So the energy level below this, which would be in this case energy level 1, has 2 electrons in it, and it's stable with 2 electrons. You're trying to get it to go away from that noble gas configuration. Right now, Be +2 is isoelectronic with helium. It's happy like that. What if we looked at a group 3 element? Let's look at boron. So boron has 3. 1, 2, 3. Let's say it costs 13 kilojoules, and I'm making these numbers up. I'm going to show you these real numbers in a second. To remove the first one, so it becomes boron +1. It takes 50 kilojoules to remove the second one and become boron +2. Are we going to see a huge jump in this next one? No, it's going to be a small jump. Let's say 100 kilojoules to remove the third one and become boron +3. Now, is it going to be a small jump or a big jump to remove the fourth electron? Huge, like ginormous. I'm making these numbers up. So, from this information, if you look at this and you see a huge jump between the third and fourth electron, how many valence electrons can you say you know this element has? That's 3. What if the huge jump was between the fourth and fifth? You know it has 4. And so that's really useful information. And the reason I'm pointing this out and kind of drilling it home is because it's on your test. You might see something that says the ionization energies for element X are 520, and then it jumps up to 7,289. Well, obviously, this is where you hit that noble gas stable configuration. Or if the numbers were 801, 2427, 3660, 25,000, look at that huge jump. Obviously, after 3 electrons, that's where you hit your stable noble gas configuration. Do you guys see what I'm pointing out here? So ionization energies, by removing one and then the next and the next, you can see where you hit that noble gas configuration. Because once it hits that, it doesn't want to lose another one. So you're going to have to pay a lot if you want to take another electron from them. Any questions? Ooh, how do we feel about ionization energy? That's like the hardest one. You just got through it. Okay, and you all know the general trend, decreasing, increasing. Next one we're going to talk about is electronegativity. This is the tendency for atoms of an element to attract electrons when they're involved in a chemical bond with another element. So I'm going to share my electron here with Ashley. Don't let go, okay? We're going to share this. It's like tug of war. I have a higher electronegativity, so I pull harder. Don't let go. I pull harder, right? So I get the electron closer to me than Ashley does. Ashley must have a lower electronegativity. If Ashley had a higher electronegativity than me, she's going to win the tug of war. She wants it more than I do. So it's like an uneven sharing. Thanks. That's what electronegativity is, the tendency of an atom to share those electrons. So, what do you think? Which elements are going to have high electronegativity? Who wants electrons more? Who wants to gain them? Who needs electrons? Non-metals do. So they're going to have high electronegativities. What about low electronegativity? Who's trying to get rid of electron? Who do you think cares less? It's like, yeah, whatever. You can win the tug of war. Metals. They're already trying to get rid of electrons, so they don't really care. This is a chart showing electronegativities. This is only your S and P block. So here's your S, here's your P. Who's left off of here? Noble gases. Why are there no noble gases on my chart? Because they don't bond. Therefore, do they want to attract electrons in a bond? No. So noble gases, none of them. No noble gases, because they do not bond. So, what's the pattern we see going across the period? So this way across, the numbers do what? They increase, and going down, the numbers tend to decrease. And this makes sense, right? So if we go down here, we go down a group, we're adding those energy levels. They're getting further and further away. It's like, how are those protons going to pull on the electrons that are way far away from it, right? But as we go across, we're adding protons, so there's more pull, so they can win that tug of war easier, right? So we put this on here. Decrease, increase, and we ignore noble gases. No. For those noble gases, because they do not bond, therefore they have no electronegativity values. Any questions about electronegativity? Let's move on to the next one then. Electron affinity, EA. This is the energy change that occurs when an atom gains electrons. So it's gaining an electron, it becomes a negative anion, right? This is the exact opposite of ionization energy. Ionization energy is how hard it was for me to steal an electron. Electron affinity is like, I'm like, hey, you want to buy this? How much would you pay me for this electron? Kind of thing. So, who do you think is going to have low electron affinity? Who's trying to get rid of electrons, therefore they wouldn't want to buy another one? Metals. And who has high electron affinity? Who's trying to gain electrons? They would probably pay a lot of money to get an electron. Non-metals, exactly. And when you look at this next chart that I'm going to show you, ignore the negative signs because it's kind of the point of view of the other atoms. But you can see that as you go down a group, 73, 60, 53, 48, 47, that the electron affinity decreases, and as you go across a period, it's a little wacky whack, but it mainly increases. So going down, it decreases, and going across, it increases. And again, these noble gases do not want electrons, so they have no electron affinity. All right, the final trend I want to talk to you guys about is chemical activity, and we're going to talk about chemical activity of metals and chemical activities of non-metals. So we're going to go ahead and look at this as two separate things. Before I say anything, obviously, we're talking about reactivity. So noble gases are out of this. They do not react, therefore they have no reactivity. All right, for metals, I want to look at it from the point of view of ionization energy, the energy it takes to lose an electron. Who, out of all the metals, has the lowest ionization energy? Who does it take the least amount of energy to steal an electron from? Look at that chart, ionization energy. Over here, who's going to be the smallest one? not lithium because it decreases going down. Fr, francium. Francium has the lowest ionization energy. And because it has the lowest ionization energy, it's basically like, I will give my electron to anybody who wants it. Don't care. It's 7 energy levels away. I'm a huge atom. Take it. Take that electron. This is your most reactive metal, is francium. Most reactive metal, francium. The closer you are to francium, the more reactive of a metal you are. So these are the next 3, then, so on and so forth. For our nonmetals, let's look at electron affinity. Remember, nonmetals are trying to gain electrons. Electron affinity is how much energy it takes to gain an electron. Who has the highest electron affinity? Who really, really, really wants to gain an electron? Decreases going down, it increases going across, so fluorine. Fluorine is going to have the highest electron affinity. Therefore, it'll pay a lot of money, in energy, of course, pay a lot of money to get another electron. Therefore, it is the most reactive non-metal. And the closer you get to fluorine, the more reactive a non-metal is.